All right, back again. Here we go. So next part of this note is going to be on the terms frequency, period, and the universal wave equation. I realize that this is awkward for you guys. It's awkward for me too. I'm sitting here in our empty classroom just talking to nobody, and it's kind of weird, but we're going to do the best we can here. All right. When an object is oscillating, it's often useful to be able to quantize the speed of the vibrations. How fast is it moving back and forth? This measure of how fast an object vibrates can be expressed as the frequency or period of the vibrations. Now, vibrates, I said vibrates here, but we can also use the word or oscillates. Spelled that right? Okay, so first, frequency. This is a measurement of the number of full vibrations, waves, or oscillations, or cycles per second. Bunch of different synonyms there that can be used. The symbol for frequency is lowercase f, and it's measured in a, you probably have heard this before, it's a kind of a weird unit. It's called hertz, symbol capital H, lowercase z. 1 hertz is equivalent to 1 full cycle in 1 second. So if you're looking at the grandfather clock, you're looking at the pendulum going back and forth. That's going back and forth at exactly 1 second. Or sorry, 1 hertz, 1 cycle every second. All right, the formula for frequency is really straightforward. If you take the number of cycles and divide it by the time in seconds. All right, for cars, they use an alternative method or an alternative notation. They use RPM, revolutions per minute, which would be the number of cycles in 60 seconds, right? Same thing. Okay, next, period. The period of a vibration is the amount of time that it takes for one full, again, vibration, wave, oscillation, or cycle to complete. The symbol for period, weird one. We've already seen this symbol. We already used this symbol before, and I didn't make these rules, but it's capital T. Same as for temperature. Okay, and it's measured in seconds. Now the formula, so for the period, it's how long it takes for that pendulum or that vibrating object to go up and down once, to do 1 full cycle. And it's just reciprocal of frequency. So period is the time divided by the number of cycles. Okay, and that's just measured in seconds. In the next little section here, we talk about the relationship between the two of them. So frequency is the number of cycles per second, and period is the number of seconds per cycle. Because of this, frequency and period are reciprocal values of each other. So here we go. Mathematically, F equals 1 over period. Frequency is the inverse of period. And period is the inverse of frequency. Okay. Natalie, stop talking. It's like, okay. I gotta break up the monotony somehow. Sorry. An engine, I have to stop myself also from asking for any questions every like 2 seconds. So let's do the first example here. An engine is running at 3,500 RPM. Determine the engine's frequency and period. All right, so the time we're going to set for 1 minute, which is equal to 60 seconds. So we want to figure out the frequency. So we've got so frequency is total number of cycles, which is 3,500. And 60 seconds. And I'm just going to pull up my calculator here and get the answer. All right, so that works out to 58.3 hertz. And we can calculate the period 2 different ways. We can actually either do 60 divided by 3,500, or we can just take 1 over the frequency. So let's do it that way. That gives you 0.0171 seconds for one cycle. So if you're actually revving your car up to 3,500 RPM, which isn't that much, it's about like, I guess if you're just taking off from the stop sign or stoplight and accelerating, it easily gets to 3,500 RPM. That means your piston inside your engine is moving up and down. It only takes 1 or closer to 2/100th of a second for that piston to go up and down inside your engine. So the engine's working very, very hard to accelerate the car. Okay, and we'll move on to the universal wave equation. So this is going to be the equation that relates it relates the velocity of a wave to its frequency and its wavelength. All right, here we go. Okay, the universal wave equation isn't a magical equation that came out of nowhere. It's actually really easy to derive just given the equation for uniform motion. Okay, so we'll start with, I'm just going to do a quick derivation and then I'll end up with the actual equation here. So if we start with velocity equals distance divided by time. All right, that's like one of the very first equations we learned in this course. If I sub in the distance being one wavelength, all right, now wavelength is the symbol we use for wavelength. It's again, going back to the previous note. Let's go back here. Wavelength is from peak to peak. Okay, that's one wavelength here. Okay, we're going to call that lambda. Okay, that's the Greek letter for it. Okay, so lambda is the symbol for wavelength. If we set the distance equal to one wavelength and the time equal to one, the period of the wave, here's what we get. And if we sub in the fact that period is a reciprocal of frequency, we end up with the universal wave equation. Where, so just let me write in, sub in f equals 1 over t. So you end up with v equals f lambda. And that's the universal wave equation. Okay, so let me just show you what, or just so you have in the notes what the variables mean. This is the velocity of the wave. This is the frequency. And this is the wavelength. Velocity is in meters per second. Frequency is in hertz. And wavelength is just in meters. All right, so that's going to relate the velocity to the frequency and the wavelength of a wave. All right, let's do an example. This example deals with light. All electromagnetic energy, including the visible light spectrum, travels in waves. I got to put a little asterisk there just for a second here. Those waves, we say that light travels in waves, but depending on the, when you get a little bit more advanced into physics, you'll see that the electromagnetic particles called photons, they can actually behave as particles and waves at the same time. But for now, we're just going to assume that they behave as waves. And the speed of those waves is always constant, 3.0 times 10 to the 8 meters per second. Determine the frequency of red light if it has a wavelength of 650 nanometers. Now, nanometer, 1 nanometer is 1 times 10 to the negative 9 meters. Okay, 1/1000th of a meter. It's just a metric prefix. Alright, so the velocity of the wave is equal to the speed of light. The symbol c, again, just like we saw last unit, it was used to represent specific heat capacity, can also be used to represent the speed of light. Okay, it's a constant. 3.0 times 10 to the 8 meters per second. The wavelength is equal to 650 times 10 to the negative 9 meters. And we want to know what the actual frequency is here. So let's plug in the values. If we rearrange this, we can just bring the wavelength variable down below the v. Oops. And plugging in the values that we know. End up with, I'm going to plug this in my calculator, 3 times 10 to the 8 divided by 650 times 10 to the negative 9 gives me 4.62 times 10 to the 14 hertz. Alright, so the light rays are oscillating very quickly. Okay, it's a super fast frequency. And that's the final answer. Okay, next. Okay, I think we've got, this is the last example. So now we're just solving for a different variable. So now we're going to see what's the wavelength of blue light if it has a frequency of 6.67 times 10 to the 14 hertz. At this point, I'd like you guys to try this on your own. So would the supply teacher please just pause this, give the class maybe 3-4 minutes to solve this on your own, and then I'll put the answer up on the board. Alright, let's take this up. Okay, the velocity is still the speed of light. The wavelength is what we're solving for, and we're given the frequency this time. Is equal to frequency times wavelength. If we solve for wavelength this time, it's just velocity divided by frequency. Frequency is 6.67 times 10 to the 14 hertz. So we end up with wavelength 3 times 10 to the 8 divided by 6.67 times 10 to the 14. So I get 4.49 times 10 to the negative 7 meters, which can be expressed as 449 nanometers. If I just move the decimal over 2 places, then I get times 10 to the negative 9. Alright, and that's it for today's lessons. Here's the homework on the bottom. Okay, and that should wrap it up. So you guys have the rest of the period to finish that homework, and we'll pick it up tomorrow on Wednesday with a new video.